In this video, we are going to discuss about Unit 4 in optical communication. So Unit 4 is nothing but optical receiver, measurements and coupling. So let us see the syllabus of Unit. So in this video, we are going to discuss about the digital receiver performance. So in that, we are going to discuss two parameters. One is probability of error, and with that, we are going to discuss about receiver sensitivity. And the next parameter is quantum limit. That is, we can just evaluate the performance of receiver just by considering these three parameters. One is probability of error, receiver sensitivity, and quantum limit. So we will consider one by one. So first comes a digital receiver performance. So the digital receiver performance that can be evaluated by measuring the probability of error and quantum limit. So what is probability of error? So in a digital receiver and the decision circuit output signal voltage, we will be considering it as V out of T. So that would be always exceed the threshold voltage when 1 is present and would be less than that of threshold when no pulse is given. So a simple approach is to divide the number of errors occurring over a certain time interval t by the number nt of pulses. That is, that pulses it may be in ones or it may consist of zeros. So transmitted during this interval. So this is called as either the error rate or we can call it as bit error rate. So which is commonly abbreviated as VER. So which is nothing but it is the ratio between NE is nothing but it is the number of errors that is occurred in certain time interval into the number of pulses transmitted during that time interval. So by taking this ratio between these two, we can able to find out the probability of error. So this is one of the way to find out or to evaluate the performance of optical receiver. So in this equation, this Bt is nothing but 1 by Tb. So as we discussed, the Tb is nothing but pulse duration or we can call it as pulse transmission rate. And here it is, and this typical error rates for optical fiber telecommunication systems are in the range of 10 power minus 9 to 10 power minus 12. So to compute this bit error rate at the receiver, we have to know what is the probability distribution of the signal at the equalizer output. So only then it is possible to find out the bit error rate. So depending on the shape only uh, we can able to say whether this 0 or 1 is transmitted at the receiver. So based upon that we can just make the decision. So here consider there are two shapes of that is shapes of two signal probability distributions. So one represents it is a probability distribution of a received logic 0 and this is a probability distribution of a received logic 1 signal pulses. So here we can from this shape of this two signal probability we can able to write the equation for the probability that the equalizer output V out of T is less than that of threshold voltage VTH when logic 1 is sent. So that can be represented as P1 of V, which is nothing but here. P1 of V is nothing but here. Here this equalizer output voltage is less than that of threshold. So this is the threshold level between these two pulses. So this is nothing but representation of logic 1 and this is the representation of logic 0 pulses. So in between that we will be fixing the threshold voltage. Now we can able to find out the probability that the equalizer output voltage is less than that of threshold. So where that is the region, that region is nothing but P1 of V. So that can be represented as integral minus infinity to V Py by 1 into dy. Similarly, the probability that the output voltage V out of T that exceeds the threshold voltage when logic 0 is transmitted. So that can be represented as P naught of V. So that will be represented by using this formula. So like this we can able to just write that equation for the probability of the equalizer output whether it is less than or greater than that of threshold voltage. Now we can just write that equation as, and if the threshold voltage is VTH, then the error probability PE is defined as sum of both the values, where this small a and small b are the weighted factors for the unbiased data with the equal probability of 1 and 0 occurrences. So in most of the application, we will be just considering it as a is equal to b is equal to 1 by 2, that is nothing but 0.5. Now let us assume that a signal has a Gaussian probability distribution function with a mean value of small m. If we sample the signal voltage level as S of t at any arbitrary time t1, the probability that the measured sample S with the time duration t1 that falls in the range from S to S plus, and which is given by f of s into ds. By using this formula, we can able to find out the sample signal voltage level. So where this f of s is nothing but probability density function, and this sigma is nothing but it is the noise variance. Here it is sigma square is nothing but noise variance, and sigma is nothing but standard deviation. So which is the measure of the width of the probability distribution. Now from this we can able to width of the probability distribution. Now what is probability of error? How to find out the probability of error? So what is that is how to find out this probability of error is that, so this probability that the noise will exceed the threshold voltage VTH, so and be mistaken as in 1 pulse. This probability of error P naught of VTH is the chance that the equalizer output voltage V of t will fall somewhere between the there is a threshold voltage and the infinity value. So that can be represented by using this equation. Similar way, the probability of error that a transmitted pulse is 1, which is misinterpreted as 0. So by that case, we can just say that the decoder electronics following the equalizer. So this probability of error is the likelihood that the sampled signal pulse falls below the V threshold voltage. Now we can able to write this probability of error for the transmitted signal is 1 pulse but 0 pulse, but it is mistaken as 1, and this is the probability of error that the transmitted 1 is misinterpreted as 0. So now we can able to find the probability of error like this. So bit error rate and the error probability P becomes this equation. Now this here, this Q is nothing but it's a parameter, so that can be represented as B on minus B off by sigma on plus sigma off, where the sigma is nothing but it's a standard deviation and B is nothing but a constant value. Now from this we can able to write this, what is this error function, which is equal to error function of x is equal to 2 by root of pi with the integral 0 to x e power minus y square into dy with respect to the probability distribution curve. So now this q value, so commonly this q value is 6, since this is corresponds to the bit error rate, which is equal to 10 power minus 9. So let us consider a special case when sigma off or sigma on is equal to sigma and b off and b on is equal to b. That is b off is equal to 0, so that the b on is equal to b. Then in that case we can able to write the threshold voltage as V by 2, that is half of the threshold, and at the same time we can able to find out the Q value as V by 2 sigma. So this Q is widely used to specify receiver performance, since it is related to the signal to noise ratio and which is very necessary to it is necessary to achieve a specific bit error rate. So it is necessary to consider the value of Q. So we will be considering that Q value as 6. Why? Because it is corresponds to the bit error rate of 10 power minus 9. Now by increasing this V by sigma by 2, then doubling the signal to noise ratio, which gives the 3 decibel power increase in the power. So at the same time, the bit error rate also decreases in the rate of 10 power 4. So therefore, there exists a narrow range of signal to noise ratio above which the error rate is tolerable, and below which a highly unacceptable number of errors that can occur. So therefore, the signal noise ratio at which this transition occurs is called the threshold level. So likewise, we can able to find out we can able to fix the threshold voltage. So receiver sensitivity. So what is receiver sensitivity? So actually to achieve this desired bit error rate at a given data rate, a specific minimum average optical power that must that must arrive at the photodetector. So the value of this minimum optical power level is called as receiver sensitivity. So receiver sensitivity, in other words, we can call it as is an average optical power in terms of decibel meter that is incident on the photodetector. So from the for the optical receiver, we can able to find out the receiver sensitivity that can be denoted as P sensitivity, which is found from the average power contained in a bit period for the specified data rate as P1 by 2, which is also is equal to Q of sigma 1 plus sigma naught by 2 into R into M, where R is nothing but responsivity, capital M is nothing but multiplication factor, and sigma 1 and sigma naught are the standard deviation for the 1 pulse and 0 pulses. And this R is nothing but it's a unity gain responsivity, which is nothing but as is equal to 1, and M is nothing but gain of the photodiode. So if it is a pin photodiode, then M is equal to 1. If it is an avalanche photodiode, then there will be a value for the capital M. So therefore, the thermal noise is independent of incoming optical signal power, but the short noise depends upon the received power. So next is nothing but quantum limit. So what is quantum limit? So here for an ideal photodetector that has unity quantum efficiency, which means theoretically we can say that unity, but practically we can say that it is less than that of unity. And at the same time which produces no dark current, which means dark current is nothing but when no light is incident and there will be a flow of minimum value of current. So that's nothing but dark current. But it produces no dark current. So there will be a minimum received optical power which is required for a specific beta rate performance. So that minimum received power level is nothing but quantum limit. So assume that an optical pulse of energy E that falls on the photodetector at one particular time interval. And this can be interpreted by the receiver as a zero pulse if no electron hole pairs are generated with the pulse present. So therefore we can write it the probability that n is equal to 0 electrons are excited in a time interval tau. We can write it as PR of 0 is equal to e power minus n bar. So where n bar is nothing but average number of electron hole pairs generated. Now from this we can able to write the average number of electron hole pairs generated. N bar is equal to eta E by HV. Okay. So here this eta is nothing but quantum efficiency and E is nothing but energy level and HV is nothing but photon of energy H into V. So the sensitivity of most of the optical receivers are around 20 decibel, which is higher than that of quantum limit. So because of the various nonlinear distortions and noise effects in the transmission link, so we'll be getting the 20 decibel, which is higher than that of quantum limit. So these are all the performance parameters of optical receiver. So only by means of these three parameters, we can able to evaluate the performance of optical receiver. So thank you for your opinion. Thank you.